Have you ever stopped to ponder the intricate cycles that dance around us, within us, and through us every single day? Our existence, in essence, is a symphony of cycles. Some are as natural as the ebb and flow of the tides, the changing of the seasons, the annual migration of birds, and even our own circadian rhythm that governs our sleep and wakefulness. Then, there are those cycles we've crafted ourselves, the rise and fall of economies, the sowing and reaping of crops, and the rhythm and melody in music. These cycles, both natural and man-made, choreograph the rhythm of our lives. Yet, beyond the confines of our immediate world, there exist cycles of a grander scale, cycles that govern the very climate of our planet. Among these cycles that shape our world and lives, there are those that subtly but significantly influence Earth's climate. Enter the stage, Milankovitch cycles. Named after the Serbian scientist Milankovitch, these cycles describe changes in Earth's orbit and tilt that cause variations in the amount and location of solar radiation reaching our planet. Let's break down these cycles into three main components. Firstly, we have eccentricity. This refers to the shape of Earth's orbit around the Sun, which changes from being nearly circular to slightly elliptical over a period of about 100,000 years. When the orbit is more elliptical, the Earth experiences greater seasonal contrasts. Next is obliquity, the angle of Earth's axial tilt. This tilt varies between 22.1 and 24.5 degrees over roughly 41,000 years. Greater tilt means more severe seasons. Finally, there's precession. This is the wobble in Earth's axis of rotation, similar to the motion of a spinning top. This cycle affects the timing of seasons and overall climate. These three cycles, working in harmony, modulate the Earth's climate over thousands of years, adding another layer to the intricate dance of cycles that shape our lives. So how do these cycles influence the climate of our blue planet? Well, as the Earth whirls through its dance in space, the Milankovitch cycles subtly shift the distribution and intensity of the sunlight bathing our world. This variation in insolation, especially at the mid-latitudes, can cause considerable climatic shifts. Imagine a world where the sunlight's warmth varies by up to 25%. This could be the difference between a temperate climate and a snow-covered ice age. These changes, though slow and gradual, have the power to drastically transform our environment over thousands of years. The Milankovitch cycles are like a celestial metronome, ticking away throughout the eons, marking the rhythm of our planet's climatic heartbeat. They have been instrumental in the onset and retreat of ice ages, the waxing and waning of glaciers, and the ebb and flow of sea levels. In the grand scheme of the universe's cycles, Milankovitch cycles play a vital role in shaping the climate of our home, adding yet another rhythm to the cosmic dance of cycles that endlessly turn around us. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Have you ever wondered why our seasons differ slightly? Why summers in the northern hemisphere are currently about 4.5 days longer than winters? And why springs are about 3 days longer than autumns? Let's delve into the mystery of our seasons. You see, our Earth orbits the Sun in a path that's not exactly round. It's close, but not quite a perfect circle. Instead, it's a shape we call an ellipse. Now imagine the largest gas giants in our solar system, Jupiter and Saturn. These enormous planets exert a gravitational pull on Earth, causing our orbit to shift subtly over time from nearly circular to slightly elliptical. This variation from a perfect circle is what we measure as eccentricity. It's a bit like if you took a circle and gently squashed it. The degree of squashiness, if you like, is the eccentricity. So the length of our seasons is influenced by this eccentricity. And as we'll see, it also affects the distance between Earth and the Sun. The changes in the Earth's orbit due to eccentricity impact the separation between Earth and the Sun. This deviation from a perfect circle is what gives us the phenomenon of perihelion and aphelion, our closest approach and farthest departure from the Sun, respectively. In the heart of winter, around January 3rd, the Earth swings closest to the Sun. This is our perihelion. Despite the chill in the air, our planet is actually receiving about 6.8% more solar radiation than it does in the height of summer. Fast forward to July 4th, and we find ourselves at aphelion, our farthest point from the Sun. Yet despite our increased distance, the difference in solar radiation is not as vast as one might imagine. Interestingly, about 23% more solar radiation reaches Earth annually, during our planet's closest approach to the sun than it does during its furthest departure when Earth's orbit is most elliptic. So, while the journey may be elliptical, the warmth of the sun remains a constant companion. Earth's eccentricity doesn't remain constant. It's part of a cycle that lasts roughly 100,000 years. Just as the seasons change, so too does the shape of Earth's orbit. Right now, our planet's eccentricity is on the decline, inching ever so slowly toward a more circular state. This might seem like a change that's happening at a glacial pace, but remember, we're talking about cosmic timescales here. In the grand scheme of things, this shift is happening in the blink of an eye. So as Earth's orbit becomes less elliptical and more circular, what does this mean for us? Well, it's all part of the subtle dance that gives us our seasons. As the eccentricity decreases, our planet will experience less variation in its distance from the sun. This means that the length of our seasons will become more uniform, and the difference in solar radiation we receive throughout the year will decrease. This cycle of eccentricity, while long, plays a role in the subtle variations we experience in our seasons. You might be wondering, does this eccentricity significantly affect our climate? Well, the answer is rather intriguing. Despite the alterations in Earth's distance from the sun, the overall variation in the annual global insolation, or the amount of solar radiation reaching our planet due to the eccentricity cycle, is quite minimal. Now you may be thinking, but doesn't a more elliptical orbit mean more solar radiation during the closest approach to the sun? True, but it's essential to remember that these shifts in incoming solar radiation are fairly balanced out throughout the year. This balance results from the fact that when Earth is closer to the sun, it moves faster along its orbit, spending less time basking in the sun's intense heat. In essence, eccentricity does play a role in the seasonal climate variations we experience, but it's a relatively minor player in the grand scheme of things. So, while eccentricity does influence our seasons and the Earth-Sun distance, its impact on our climate is relatively minimal. The subtle dance of our planet around the sun continues, always changing, always fascinating. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Have you ever wondered why we have seasons on Earth? It's all about the tilt. This tilt, scientifically known as obliquity, is the angle of Earth's axis as it spins on its merry journey around the sun. Picture a top spinning, slightly tilted, not perfectly straight up and down. That's our Earth, a cosmic top spinning through the universe. This tilt, however, is not constant. Over the past million years, it has wavered between 22.1 and 24.5 degrees. These fluctuations might seem insignificant, but they have a profound impact on the intensity of our seasons. The greater the tilt, the more extreme our seasons become. Why? Because each hemisphere receives more solar radiation in the summer when it's leaning towards the sun, and less in the winter when it's leaning away. So in essence, the tilt of our planet determines how much sunshine we get. So, the next time you feel the warmth of the summer sun or the chill of winter, remember it's all about the tilt. You might be surprised to learn how much Earth's tilt, or obliquity, impacts our lives. Let's delve into the fascinating effects of Earth's obliquity on our seasons. Imagine Earth as a giant spinning top. As it spins, it also tilts, and this tilt, or obliquity, is what gives us our seasons. The greater the Earth's axial tilt angle, the more extreme our seasons become. Why? It's all about the solar radiation each hemisphere receives. During the summer months, the hemisphere that's tilted towards the sun receives more solar radiation, leading to warmer temperatures. Conversely, in the winter, the hemisphere that's tilted away from the sun gets less solar radiation, resulting in cooler temperatures. So the larger the tilt, the greater the difference in solar radiation, and the more extreme our seasons. But Earth's obliquity does more than just give us warmer summers and colder winters. Greater tilt angles are also advantageous during deglaciation, which is the melting and retreat of ice sheets and glaciers. When Earth tilts more towards the sun, the increase in solar radiation helps to melt these large ice masses, a process that's crucial in shaping our planet's landscape. However, the effects of Earth's obliquity aren't uniform globally. Areas farther from the equator experience a smaller change in total solar radiation than do higher latitudes. Think of it this way: the closer you are to the equator, the less of an effect Earth's tilt has on your seasonal temperatures. But the closer you get to the poles, the more dramatic the impact. So, Earth's obliquity doesn't just change the intensity of our seasons, it also influences the distribution of sunlight, the melting of ice, and the shaping of our landscapes. It's a subtle force, often overlooked, but it plays a fundamental role in our planet's climate and geography. Earth's obliquity doesn't just give us our seasons, it shapes our world in profound ways. So, what's next for Earth's obliquity? Well, the current tilt of Earth's axis sits at about 23.4 degrees, which is roughly halfway between its known extremes. This tilt is on a slow, gradual decrease over a lengthy period of 41,000 years. Looking ahead, we can predict that in about 10,000 years our planet will reach its minimum tilt. This shift will lead to milder seasons, with winters becoming warmer and summers cooler. This might sound pleasant, but remember that these changes have significant implications for our planet. The gradual increase in warmth will allow snow and ice at high latitudes to accumulate into large ice sheets. These ice sheets then act as giant mirrors, reflecting the sun's energy back into space and causing even more cooling. So, as we look to the future, we can expect our world to continue to change, all thanks to the tilt of the Earth. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Have you ever pondered about the spinning globe we call home? How does Earth's rotation impact our day-to-day existence? To understand this, we need to explore two intriguing concepts: axial precession and apsidal precession. Consider a spinning top. As it spins, it wobbles slightly off-center. Similarly, Earth also wobbles on its rotational axis due to tidal forces caused by the gravitational pull of the Sun and Moon. This wobble, known as axial precession, alters Earth's rotation and makes it bulge at the equator. The direction of this wobble, relative to the fixed positions of stars, changes over a cycle of approximately 25,771.5 years. Axial precession influences our seasonal contrasts. Currently, the southern hemisphere experiences perihelion, or the point where Earth is closest to the sun, in summer. This results in hotter summers. The northern hemisphere, on the other hand, experiences perihelion in winter, leading to more moderate seasonal variations. But hold on. In about 13,000 years, axial precession will reverse these conditions. Earth's precession also affects the timing of seasons relative to our planet's closest and farthest points from the sun. However, due to our seasonal-based modern calendar, we won't see winter in July in the northern hemisphere. Interestingly, our North Star has also changed over the years due to precession. A few thousand years ago, Kochab and Ferkad held this title. Today, it's Polaris and Polaris Australis. Now let's dive into apsidal precession. Like a spinning top, Earth wobbles not only on its rotational axis, but also along its orbital ellipse, the oval-shaped path it takes around the sun. This wobble, primarily influenced by Earth's interactions with Jupiter and Saturn, takes about 112,000 years to complete a cycle. This apsidal precession alters the orientation of Earth's orbit with respect to the ecliptic plane. When axial and apsidal precession combine, they produce an overall precession cycle that lasts on average 23,000 years. In essence, precession is a subtle yet constant reminder of our planet's dynamic nature. It influences our climate, navigational systems, and even our perception of the night sky. So the next time you gaze up at the stars, remember, our place in the cosmos is far from static. We're part of a grand cosmic dance, waltzing to the rhythm of precession. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. We are grateful to NASA, JPL, and Caltech for their diligent work in creating the 3 animations we have displayed, which illustrate various Milankovitch cycles. Please share your thoughts about these cycles in the comment section below. Do you believe that these are a contributing factor to the overall change in the weather? Or do you believe that humans are to blame? Do you believe that our emissions and other factors also affect the way that nature's cycles operate? Thank you for observing. Your opinions on this video and, if any, your thoughts on our influence on the cycles would be greatly appreciated. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content.